All right, so let's do a triple integral and do it in spherical. All right, so we've got the triple integral over E 16z dv, and E here is the upper half of x squared plus y squared plus z squared equals 1, which we were just talking about. All right, and we're going to use spherical coordinates for this. Or evaluate using spherical coordinates. All right, so just like cylindrical coordinates, we need to convert that to z over to, of course, we'll convert that over to spherical, but there's also a conversion we need to talk about with dv, and so you can develop it. It's like cylindrical, a little more complicated, a little more, one maybe extra part, I guess you could say. dv for spherical if we put that in spherical, dv is rho squared sine phi, and then the usual order is d rho, d theta, d phi. So in other words, when we convert from this, which is basically in just your Cartesian form there, but when we go to replace dv, it's going to, we're going to use the rho, the d rho, d theta, and d phi, but you got to put in a rho squared sine phi in addition to that, and that's just because of the way it all works here. Okay, so here we obviously will have then 16 and z, remember z is rho cosine phi, and then dv is rho squared sine phi d rho d theta d phi. Okay, but we still need to put in our limits to the integration here, so we got to figure this out. All right, so let's work on E. E is the upper half of, and this is why this one is probably best in spherical, because what do we have right here? The upper half of a sphere, right? Radius 1 sphere, 0, 0, center at the origin. And so that definitely lends itself to spherical there. Well, let's start with rho. It's the easiest one. Rho and theta are not too bad. So rho, again, you have to remember what rho is. Rho is from the origin up to the surface. So, and that's why in this case, we're talking for E here, the upper half of our radius 1 sphere, all right? And so we're going the inside here of that sphere. What is rho? What are the values rho ranges from? Well, you start at the origin. Obviously, rho can be 0, but then it goes out to the surface, which the surface, how would we write that in terms of rho? Well, again, this right here is rho. So another way we could write this is rho equals 1, rho squared equals 1, so rho would also equal 1, square root of 1. So wouldn't that just mean rho goes to 1, 0 to 1? So that'll be our limits for rho. Theta, easy enough. Theta is the xy plane, the angle in the xy plane we go through. Well, if you look at the xy plane, or just think about z squared equals 0 here, we've got a circle, radius 1, x squared plus y squared equals 1. So if we just look at that, theta is the angle we go through, so we go through the full 360, right? 0 to 2 pi. With me? Okay. All right, now, so if you think about this, so now all that's left is phi, right? What values of phi do I range through here? So this was actually a fairly nice one. So phi is the angle that we make with the positive z-axis. And so if you think about all the points on this, or in this sphere here, half sphere, upper half, what angles of phi do we have? Well, one way to think of it, if you look at maybe the x, not the x, the yz plane, we would just have the top half of a radius 1 circle. And what that does is, yeah, you can look at, if you look at a point on the surface, you can look and see, well, what are my angles going through for phi there? Remember, phi starts at 0, we go 0 to possibly pi, but in this case, we don't go to pi, do we? Where do we go to? 0 to pi over 2. So, anyway, it takes a little, maybe, getting used to there, but theta, this is your theta angles in the xy plane, good way to look at it, and phi is the yz plane. You don't go backward in this case. You start at 0, and then go through the angles there. All right, so that would mean, here's what we triple integral works into. 16, all right, so we've got what, rho cubed and cosine phi, sine phi, d phi, d phi, d theta, d rho, d theta, d phi. Okay, so we do them in this order. Rho's first, so we go 0, 1. Theta's next, 0 to 2 pi. And phi is last, so 0 to pi over 2. So it's fairly nice, because in this case, there's no real variables in the limits are just constants. Right? So that's nice, and we could break this triple integral up into 3 separate integrals, but I don't think it's too bad to just go through them if we do one by one here. All right, so the first one, integrate with respect to rho. Well, we've got rho to the third. So the antiderivative would be rho to the fourth, 1/4 times 16, that would be 4, rho to the fourth. And of course your cosine phi and sine phi come along for the ride. And then evaluate that from rho equals 1 to 0, or 0 to 1. Then we'll do the theta and the d phi. that's pretty nice because rho equals 1 would just give me 4, rho equals 0 give me 0, so it's just 4 cosine phi sine phi. Like I said, this one's not too bad compared to some of the other ones we've come across, all right? So now we're doing the integral with respect to theta. Well, there's no theta in that, so we'll have, of course, the integral still to do with phi, but the integral here is actually, it's just 4 cosine phi sine phi, and that's a value times theta. And that's evaluated from 0 to pi, 0 to 2 pi, right? That's our theta limits, 0 and 2 pi. Yeah, so those go in for theta, so it'll just have what? That'll be 8 pi. 2 pi there, 0, 0. So 4 times 8 pi cosine phi sine phi. Just have to keep theta and phi separated there. So far, so good. And so the first two integrals have been very easy. We saved the best for last here. And we talked about one way. The book likes it to do this one way, but really this can be done with U substitution. U equals sine phi. Du is then cosine phi d phi. So you've got, that's u, and then that's du, so you got just 8 pi. That's u, and these two are du. So another way you can do it. The book likes to change this to the double angle. That would be half of sine of 2 theta or something. Sorry. I can't keep my thetas and phi straight. But that's another way you can do it, but you're still going to have to use U substitution on that. So either way you go. All right. So yeah, that's just 8 pi times 1/2 U squared. Oops. Now we integrated it. But we want to evaluate it for phi, so that's sine squared phi. That from 0 to pi over 2, and so that's 4 pi, and then you got sine squared pi over 2 minus 4 pi sine squared is 0, which that's 0, and sine of pi over 2 is 1, so 4 pi. Anyway, about as easy as triple integrals you can get there. As you probably come to realize. All right. All right. Anything question-wise on that one? So good. All right. On this one, we want to evaluate. We'll just set it up by changing it over to spherical. Convert. Spherical. I guess we kind of were doing there, but this one's already got the limits and everything, so. All right, so 0, 3 is the first limit, 0 to the square root of 9 minus 1 squared. And then square root of x squared plus y squared to square root of 18 minus x squared minus y squared. And the rest of it, we got x squared plus y squared plus z squared is the function we're integrating, triple integrating. And dz, dx, dy is the order there. Leave that there for a second. Okay. Well, let's first of all just look at what we got here. All right, so with this order that we've got, the z's come first, so z is between the lower limits x squared of x squared plus y squared, and then the upper limit is 18 minus x squared minus y squared. All right, then the x's are next, so x goes from 0 to the square root of 9 minus y squared, and then y's go from 0 to 3. Okay. Well, we've encountered, let's start with these first of all. So that focuses us on the xy plane again. So in the xy plane, the region we're integrating over, what does this describe? And so I think we've done this a couple of times now. So this is our function. Our function is x equals the square root of 9 minus x, square root of 9 minus y squared, and then x equals 0, of course, is the y-axis. But yeah, we've seen that a couple of times now. That's a semicircle, but half of it, and in this case we're talking which half? X equals square root of 9 minus y squared. It's the right half, right? This is the right half of a circle. You know, if we have y equals the square root of 9 minus x squared, that's the top half of a circle. This is the right half of a circle, because it's in the x equals 1 half. So we've got a radius 3 circle, and it's the right half, so it goes from negative 3 to 3. But in this case, we're not talking the full semicircle there because of this. Whoops, negative on top, negative on the bottom there. All right, what does that tell me? Well, that tells me I'm actually not dealing with the right half of a circle. Y is only going from 0 to 3, so I'm only talking the sector in the first quadrant of a circle. With me there? All right. Well, what does that give? That gets me theta. Remember, theta is the angle in the spherical coordinates. Theta is the angle in the xy plane. So what in the xy plane am I dealing with here as far as theta goes? Well, theta goes from 0, right? That would be theta equals 0 to this angle here, which is pi over 2, right? You ever get that? So in spherical, we're going to go theta 0 pi over 2. Okay, now the others, the rho and the phi. We're going to have to deal with these two little things right here. So let's talk about, first of all, z equals the square root, the lower bound. Z equals the square root of x squared plus y squared, which we may have talked about before as far as shape goes, but probably should talk about it again. Probably the easiest way to go through it here, since it's maybe been a while, is think about level curves. You know what I'm talking about there? Different values of z. Of course, we're talking positive values of z here, since it's got to be square rooted, only positive values. So z could equal 1, that would be 1 equals the square root of x squared plus y squared. Well, square both sides. You're talking a circle, aren't you? So when z equals 1, we've got a circle. When z equals 2, what do we got? Well, square both sides. We're talking a circle, but radius 2. And then, so I think you can see the pattern there. Yeah, that's going to be circle radius 3. So forth. So as you go up on your z-axis here, so z equals 0 would obviously be 0, but at z equals 1, we've got that circle, that level curved circle, so it's a radius 1 circle. At z equals 2, we've got a radius 2 circle. At z equals 3, we've got a radius 3 circle. So what we wind up with there is it's a cone. It's a cone. So that's the lower half of the z values. The upper half of the z's, upper part, let's say, and a half. You got z equals the square root of 18 minus x squared minus y squared. Well, that's obviously different than a cone. This is what, that's going to be a cone. This one actually is better if we look at squaring both sides. Which I guess we could have done that one, but that one wouldn't help us as much. You square both sides here, do you recognize what that is? Think about moving the x squared and the y squared. Add the x squared and the y squared to both sides. What do you got? That's a sphere, right? And the radius is square root of 18, 3 square root of 2, however you want to phrase it there, but 0, 0, 0 center. Yeah, but we started with this, and what does that tell me? We're just talking the top half, right? That's the top half. So this is the top half of the sphere. Okay? All right. So imagine then, all right, so radius is, it's a little over 4, right? So we've got this, so our z's are going to go from this cone, that's our lower limit, up to the sphere, which is radius 4 sphere. So we're going from that cone up to that sphere, right? That's what that's telling for the z. Z goes between those. All right, well, if you look at that again and just, well, for that tells me rho. Again, rho, we're going to spherical coordinates, so that's, we got a sphere involved here, it makes sense. What would that tell me about the rho? Well, rho is going to range from 0 up to that sphere, isn't it? Which, what would that mean rho goes between? 0 and, well, remember, a sphere, so that's x squared plus y squared equals z. That's also rho squared equals 18. So rho goes up to the square root of 18 again, doesn't it? It goes from 0 up to the outer of the sphere, or the surface of the sphere, which is square root of 18. Yes? Now again, for me it helps for phi to think the YZ plane. That's what helps me to get phi. All right, so notice here, if you think about the YZ plane, I've kind of got it drawn here. This is what we're talking about in the YZ plane, this little, like a piece of pie there. With me there? Because that cross section, if you will, cut it in the YZ plane. You're just going to have that sphere and then your V shape there. Okay, so what is phi? Well, it looks like phi is going to go from 0 to whatever angle that is. Which is not a nice one like we've always had so far. Usually we've had, 0 to pi over 2 or so this is a good one for that purpose, just to show us how we can get at it. Well, what we can do is utilize, so how do we get this angle here? Well, it's all locked in with that intersection point. And so we're looking at the intersection basically between these two curves. And I think, this curve is, well, there's a couple ways we could go. So to figure this out, we need to figure out the intersection of z equals the square root of x squared plus y squared, and z equals square root of 18. 18 minus x squared minus y squared, but probably a better format if we go to this z squared equals x squared plus y squared, and here's z squared equals 18 minus x squared minus y squared. That's probably a better form to figure out this intersection. Like I said, a couple ways we could go. We could substitute a couple of ways here. Actually, the preferred form probably on this one is this right here. So let's go ahead and make it x squared plus y squared plus z squared equals 18. And then, the easiest way to go here on this one is notice that z squared equals x squared plus y squared. So I can, for x squared plus y squared, I can substitute this z squared right here. So I have z squared plus z squared, so that'd be 2z squared equals 18, which would be z squared divided by 2 equals 9, which we're talking positive z, so z equals 3. We're almost there. So the intersection is where z equals 3. Well, that may not do me any good, because what I'm looking for is the intersection angle, if you will. So let's convert that to spherical. Z is what? Rho cosine phi. So we finally got our cosine involved there. Well, we know the rho is square root of 18. I know that for sure. Or intersecting there. So cosine phi is 3 divided by square root of 18. Which may not ring a bell, but if we change that to the 3 square root of 2, 3's cancel, so that's cosine phi equals 1 over the square root of 2, which that's cosine phi, same as square root of 2 over 2. So what's phi? It's pi over 4, isn't it? So phi is going to range from 0 to pi over 4. So So that's just to get the limits. The rest is actually easier than that. All right, so I got my limits here, here, and here. So my integral, let's just do it right here. All right, so I'm going to change to spherical here. Well, this is nice. X squared plus y squared plus z squared, what is that in spherical? Just rho squared, right? And then dz, dx, dy, that's the same as dv. And that's why I left this up here. And dv is rho squared sine phi, d rho, d theta, d phi. With me? And so then I can put on my limits. All right, so d rho, rho's first. Rho is 0 to the square root of 18 or 3 square root of 2, whichever you prefer. D theta, theta is 0 to pi over 2. And then last but not least, d phi, which is 0. Okay. So that's just so we can get it where we can evaluate it. So I would guess that's the easy part, this. Evaluating it. Question? But I just wanted to convert it to. So some of these you don't have to actually have to evaluate.
Actually, then.
Yeah, you just
Thank you.
just convert.